Hey everyone, and welcome back. When we last met, we built and tested the new ALU adder board where we were also able to squeeze in some controls like the 3 to 8 function decoder, the 0 detect, and the 3 ALU conditions registers. But what we didn't have was the space to include the ALU logic functions, and that's why we're here today. The ALU has two inputs driven from the B and C registers, and these feed into both an 8-bit adder and an 8-bit logic unit. The ALU also contains a 3-bit function decoder, which sends the appropriate signals to the adder or logic unit depending on which instruction is being executed. And finally, the ALU also manages the carry, 0 detect, and sign condition registers. In the previous video, we finished the 8-bit adder and were also able to squeeze in those other control circuits on that same card. So now, let's finish the ALU by building the 8-bit logic unit. Within the ALU, the function decoder converts the binary 3-digit input into the appropriate control signals. The first 3 of these are used by the ALU adder and control card we built previously. And now, we need to work on these 4 logic gates, as well as this shift left circuit. So let's start with a quick overview of the logic gates. Here's the truth table for the AND gate, and as the name implies, the output is high only when both B and C inputs are high. The OR gate, on the other hand, will produce a high output when B, C, or both of the inputs are high. Next is the exclusive OR, and the truth table looks a lot like the one for the OR gate, except that if both B and C inputs are high, it produces a low output. The last of our logic gates is the NOT gate, and this gate simply inverts the input signal so that a low input becomes a high output and a high input becomes a low output. Now this last function isn't a logic gate, but rather it's a circular shift left function, and it takes the 8-bit value being fed from the B register and shifts it 1 bit position to the left, with the value that was in bit 7 being moved to bit 0. And this is a lot like the ROL or rotate left instruction on a 6502 processor, except that it doesn't do anything with the carry. But that might be something to think about in this design. So let's start with the elegant 1-bit logic circuit designed by Dr. Harry Porter that encapsulates these logic circuits into 2 4-pole double-throw relays. And I also find the information at Paul Law's Relay Computer blog a huge help as I translate the schematics and convert to the double-pole double-throw relays that I'm using. So here's the completed prototype for our 1-bit logic circuit, which includes these B and C input lines, and then all of these LEDs representing the various outputs. And we'll start with the green LED tucked under here, which represents the AND output. And then above that, we have the yellow LED representing the OR output. And then this blue LED represents the exclusive OR. And finally, on the other side, we have the NOT and the shift left outputs that are driven by the B input only. And since we have 2 inputs, it means that there's 4 possible output states for this circuit. So right now we can actually see the first state, which is that B and C are both low or 0, and because it's low, the NOT output is high. So I'll go ahead and hook up the B input, and we can now see that our second state shows the OR, the exclusive OR, and the shift left outputs are high, but the NOT is now low, which is correct since the B input is high. Now, moving on to our third state, I'll disconnect B and plug in the C input, where we now see the same outputs for the OR and exclusive OR, but because B is disconnected, we're back to showing the NOT as high and the shift left as low. And then for our final state, I'll connect B and C, which now gives us the AND output as well as the OR condition. And we also see that the exclusive OR is now low. Then finally, we have the expected NOT and the shift left outputs since the B input is high. So this 1-bit logic circuit gets a pass. Based on the current design, we will need 32 relays for the logic units and another 20 relays for gating. And I also want to have all of the logic outputs visible at all times, which means a lot more LEDs and resistors. Now so far, it's not that crowded, and we've even had more relays on other cards. But the big consideration here is the number of traces. We'll need 16 lines for the B and C inputs that need to reach each of the 32 logic relays. Next, each of the potential logic outputs needs to run to the respective gating relays, and then we'll need to connect all of that to the 45 output LEDs. We'll also need to run the 8 data bus lines to each of the 5 sets of gates, and then the control lines to activate those same gates. And lastly, we need to provide the power source to the logic relays. And when viewed like this, we can see that the trace routing for this card will be daunting to say the least. Now, there's no way to reduce the number of gating relays, but let's see if there are some creative options for the logic units. Going back to the schematic, the first thing that comes to mind is that I could use a couple of diodes in place of the OR gate. Next, I switched the AND circuit to where the OR circuit used to be, which now frees up the pins needed to move the exclusive OR circuit to the bottom 2 relays. Finally, we can piggyback the NOT to pin 6, and the shift left can be pulled directly from the B input. And what we're left with is a new 2-relay version of the 1-bit logic unit that hopefully gets the job done. So here's the revised and condensed version of the 1-bit logic circuit, which is now down to 2 relays, plus these 2 new diodes down in between them that represent the original OR logic circuit. And the LEDs have changed position as well, but I've used the same colors to represent the various outputs, so it should be fairly straightforward to test just by visually comparing the 2 circuits in action. So we'll quickly run through those same tests that we ran previously and see if we come up with the same results. And starting with the B and C inputs at 0, we're off to a good start, as we're seeing the matching NOT output on both versions. So we'll connect the B input on the original circuit, and then the B input on the new version, and it looks good. We have our matching exclusive OR, as well as the OR and the shift left outputs. And also, our AND and NOT outputs are both low as expected. So we can disconnect the B inputs and then connect both C inputs. And again, we see the matching outputs for both versions, so this is great. And now for the final test, which is to connect the B and C inputs on both. And drum roll, please. Yes, we have the matching outputs on both the original and the new version of the 1-bit logic circuit. So things are looking really great, and you may be wondering, well, why did this original circuit use 4 relays to begin with? And there's actually a really good reason for this, which is because this original version prevents what's known as backfeeding. And I'll flash up this simplified animation that hopefully explains this a bit further, which includes a logic circuit with the B and C inputs, a couple of gating relays, and the data bus. So whenever we are gating a value to the data bus from any of our cards, the assumption is that the data bus is empty, or in other words, doesn't contain a value. However, if for some reason there was already a value on the data bus when we enable the same gate, the higher values, which are really voltages on the data bus, will always override the 0 or lower voltages, and in the right circumstances, this can result in a backfeed. And just to make things even messier, because the gate is open, This same backfeed can even cause further problems upstream of the original output. So I can actually demonstrate how backfeeding might be a problem with this new version of the circuit by providing a voltage to our exclusive OR output line. Now, when B and C are 0, this doesn't seem to cause a problem aside from creating a high value on the output line itself. But in a specific situation, the backfeed would occur when the B and C inputs are high, because it actually shifts the NOT output to high when it should be low. And this is because in order to condense this circuit, I needed to share a pin on this relay. And aside from the outputs to the data bus, we also need to consider this shift left output. In Harry Porter's original design, he also had this output driven from the B input directly, and he even mentioned the possibility of backfeeding. But when I look at the revised version by Paul Law, he addressed this by using an unused normally open pin on this relay. However, in order to condense this circuit to two relays, I've needed to tie the shift left output back to the B input. But fortunately, in this particular case, we're already using these diodes on the ALU output lines for the B and C registers. So I really racked my brain about this, and I am convinced that this particular case of backfeeding is very unlikely to happen, because if there is data on the data bus when there shouldn't be, then that's really a problem with the instruction microcode as opposed to something to be solved for with more diodes. Now there is one last piece to this dilemma, I promise, but it's just the fact that I would be reducing the number of relays, and in a relay computer, that would mean less clicking and clacking. And just for fun, I put it out as a vote on the channel, just to see what everyone thought about reducing the number of relays on this board. And 80% gave a thumbs up to proceed with the 2-relay version and some diodes. So thank you all for taking the time to vote on this. And now we can move on to the next steps, which is to wrap up the schematics and complete the PCB design. Thanks to the magic of editing, these videos make the design phase look like a few minutes of work. But even with the reduction in relays, it still took me a few iterations and several hours to find the routes for all of these traces. But once that was done, the next part was easy. With just a few clicks, it was off to PCBWay. And a week later, the finished prototypes arrived. Every time I get one of these packages, it makes me feel like a kid all over again. And I love how they always throw in a few fun things that I can stick on other things. And besides circuit boards, PCBWay has many other services, like 3D printing, CNC machining, and even injection molding. So check out PCBWay when you're ready to create your next awesome project. So as I always do, I typically pause after I've populated the first few relays and diodes, as well as a row of LEDs, just so I can test things and make sure that things are working before I proceed with populating the rest. So I've hooked up a couple of power leads. So I think that we can go ahead and just start testing really quickly with this first, I guess, least significant bit of the logic outputs. And we start with the NOT bit being lit at the LSB, which is correct because there's no input on the B. And if I just apply a voltage to B, we see that we now have the NOT value is 0, but the XOR and the OR indicators are now on for that bit. So that is correct. And while I'm at it, I'll now apply some voltage to the C bit, and we see that the NOT value is now high, which is correct because there's no voltage on B input, and we have the exclusive OR and the OR values correct. And the only one that's not lit is the AND and the shift left. So we'll start by looking at the AND, and to test that, we'll just actually supply a voltage to B and C. If I can do this, and I can't point at it, but it looks good. We have our AND high and our OR value high as well, an exclusive OR, and the NOT values are now low. So that is fantastic. And I think the last one to touch on is this shift left, which is really a shift left circular. So this should be lit if the MSB of the B input is high. So I'll just quickly touch that. And yes, we see a high input. So there's more to come on that. We just have to make sure that everything else is wired correctly as we move along. So I might do some periodic testing as I fill it in, but I think I'm good to go. Now you may have noticed this extra jumper LED and even this extra relay here. And earlier we talked about the shift left circular operation, also known as the rotate left, which simply rotates the B value. But sometimes it's handy to also be able to capture the most significant bit as it's being rotated. So I've added this extra circuit so that when this jumper is closed, the most significant bit will be captured as the carry bit that can then be stored on the conditions register in the ALU control card. And I can quickly show this by activating the MSB and then the shift left control line. And we can see that the carry bit now goes high. But if I remove the jumper and perform the same operation, it should show as low. The final piece of this build is now to attach the IDC connector. And then I just need to add another connector on the 16-pin ribbon cable so that the new logic card is daisy-chained to the adder and the B and C registers. And for our test setup, I'm using the Arduino knockoff with two 8-channel relay modules. So we've officially completed the ALU, at least enough to do some basic math and logic functions. And when we look back at the overall architecture, we can see that we're making excellent progress. And I think it's now time for our relay computer to start executing some code. And since we already have this instruction register and the prefetch microcode, we get to dive right into building the instruction decoder and controller card. And we'll get to that in the next episode. So with that, thank you so much for following along on this journey, and I'm looking forward to seeing you next time.